The universe you see is only a fraction of the full picture. Behind the stars and empty space, an invisible architecture dictates everything that happens. These are the hidden fields of the cosmos, the fundamental operating system of reality itself. From the gravity that holds you to the Earth to the strange quantum foam at the smallest scales, these fields are the true rulers of the physical world. By the end of this journey, you will know 30 of the most incredible theories about these hidden dimensions of existence. We will explore how a single field could erase the universe in a vacuum decay, and why time itself might be an illusion emerging from another. What is the one cosmic mystery you hope these fields will finally explain? Our journey begins with the one hidden field we have actually found. The Higgs field permeates all of space like an invisible cosmic molasses. To understand its power, picture a quiet party where guests mingle freely. Suddenly, a famous celebrity walks in. The crowd immediately clusters around them, slowing their movement through the room. In this analogy, the party guests are the Higgs field, and the celebrity is a fundamental particle. The act of the crowd clustering around the celebrity is what gives that particle its mass. Some particles, like photons of light, are like anonymous guests who slip through the crowd completely unnoticed, remaining weightless and moving at the speed of light. Others, like the top quark, are the biggest celebrities of all, acquiring immense mass as they interact with the field. This elegant idea was the brainchild of physicist Peter Higgs and several others in the 1960s. For decades, it remained a beautiful but unproven theory, a ghost in the cosmic machine. Proving its existence required one of the most ambitious experiments in human history. Deep beneath the border of France and Switzerland, the Large Hadron Collider at CERN smashes protons together at nearly the speed of light. Scientists sifted through the debris of countless collisions, searching for a tiny ripple in the Higgs field itself, a particle that would be the proof. In 2012, they announced their historic discovery, the Higgs boson. This was not just the discovery of a particle, it was the first direct evidence of the invisible field that gives our universe its substance. Without the Higgs field, nothing would have mass. Electrons would not orbit atomic nuclei, atoms could not form, and you, the Earth, and every star would simply fail to exist. The stability of this field is what allows matter to be, but what if that stability is an illusion? The Higgs field might not be resting at its most stable state. It could be perched in a fragile, false vacuum, like a ball balanced on the rim of a bowl. A random quantum fluctuation could, in theory, knock this ball into a deeper, more stable valley of energy. This event, known as vacuum decay, would create a bubble of a new universe with different physical laws. This bubble would expand at the speed of light, rewriting reality as it goes. One moment, the universe would be as it is. The next, everything from atoms to galaxies would be erased into a new, alien state. The field that gives us existence could also be the instrument of our ultimate end. The stability of the Higgs field is just one layer of a much deeper cosmic ocean. To truly grasp the universe's hidden architecture, we must dive into the quantum realm. Here, the very idea of a solid particle dissolves into something far more fluid and strange. Quantum field theory reveals a universe that is not made of tiny, separate balls, but is instead a vast, seething ocean of invisible fields. Every single point in space, from the void between galaxies to the air in your lungs, is filled with these fundamental fields. There is an electron field, a quark field, a photon field, all overlapping and permeating all of reality. What we perceive as a particle is not a tiny speck, but a localized vibration in its corresponding field, like a wave rising from the sea. Picture a perfectly calm lake, its surface smooth and still. This is the field in its lowest energy state. Now imagine a single drop of water falling. It creates a ripple, a localized disturbance that travels across the surface. That ripple is a particle. An electron is just a tiny knot of energy in the universal electron field. A photon is a shimmer in the photon field. Even more mind-bending is that when a particle and its antiparticle meet, they annihilate. In our lake analogy, this is like a crest and a trough meeting, cancelling each other out and returning the surface to calm. The particle vanishes, its energy smoothly dissipated back into the field from which it came. This revolutionary perspective successfully merged the chaotic rules of quantum mechanics with Einstein's theory of special relativity, creating the most accurate and powerful framework in all of physics. It tells us that the solid, predictable world we experience is an illusion, emerging from the constant, vibrant hum of these hidden fields. Every sight, every touch, every star in the sky is the visible music of this cosmic symphony. But if fields are the true fabric of reality, what happens when that fabric is stretched to its absolute limit? While the quantum fields dictate the behavior of the small, another hidden field governs the grandest scales of the cosmos. Einstein's theory of general relativity completely reimagined gravity, stripping it of its identity as a simple force. Instead, he proposed that gravity is the geometry of a unified entity called spacetime. Picture spacetime not as an empty stage, but as a vast, flexible trampoline sheet. The sun, a massive bowling ball placed in the center, creates a deep, smooth depression in this fabric. Now roll a marble representing Earth across the sheet. It does not travel in a straight line. Instead, it follows the curved path created by the sun's indentation, forever orbiting the central mass. This curved path is what we experience as gravity. The Earth is not being pulled by an invisible string. It is simply following the most natural route through the warped geometry of spacetime. Every object with mass or energy contributes to this curvature, from a planet to a person. This gravitational field is the true, invisible architecture of the universe, dictating the motion of everything from falling apples to the orbits of entire galaxies. Yet, this beautiful theory presents physics with its greatest unresolved conflict. General relativity describes the cosmos on a grand scale with perfect elegance, but it is a classical theory. It knows nothing of the frantic, probabilistic world of quantum fields. The challenge of quantizing gravity, of finding a single theory that unites the immense and the infinitesimal, remains the holy grail of modern physics. For decades, evidence for this cosmic curvature was indirect. Then, in 2015, a new era of astronomy began. The LIGO Observatory detected for the first time gravitational waves. These were not mere vibrations in the air, but literal ripples in the fabric of spacetime itself, created by two black holes colliding over 1 billion light-years away. The detection was like finally hearing the sound of the cosmos, a faint chirp confirming that the gravitational field is a dynamic, living entity that can stretch and compress, carrying energy across the universe. The ripples in spacetime are echoes of a much more violent event. For the universe to stretch and warp in this way, it must have begun with an expansion of unimaginable ferocity. This leads us to a field so powerful it could shape the entire cosmos in an instant. The theory of cosmic inflation proposes that a fraction of a second after the Big Bang, a hypothetical field, the Inflaton Field, dominated reality. It was trapped in a state of high energy, a false vacuum, and this state possessed a bizarre property. Instead of pulling things together, it generated a powerful repulsive gravity, causing space itself to expand at an exponential rate far faster than the speed of light. In less time than it takes to blink, a subatomic speck of universe was blown up to a size larger than our entire observable cosmos. This incredible growth spurt solves two profound mysteries. The first is the horizon problem. Look at the night sky in opposite directions. The regions of space you see are so far apart that light has not had time to travel between them since the universe began. Yet they are the same temperature. How can two things that have never been in contact be so perfectly uniform? Inflation provides the answer. They were in contact. Before the rapid expansion, all parts of the observable universe were crammed into a tiny, connected region that had time to equalize its temperature. Inflation then stretched this uniform region across the sky, locking that sameness into place. The second puzzle is the flatness problem. Measurements show the geometry of our universe is incredibly flat, not curved positively or negatively. For the universe to remain so flat after billions of years, its initial conditions had to be fine-tuned to an absurdly precise degree, like balancing a pencil on its tip for eons. Inflation naturally explains this. Think of how the surface of a balloon flattens out as you blow it up to an enormous size. No matter how wrinkled it started, a tiny patch becomes seemingly flat. The violent expansion of the universe did the same thing, stretching the fabric of spacetime until any initial curvature was smoothed into the flat cosmos we observe today. But this explosive growth could not last forever. The Inflaton Field was unstable, perched in that false vacuum state. Eventually, it decayed, rolling down its energy landscape to a more stable, lower-energy valley. As it fell, the enormous potential energy stored in the field was released in a torrent, flooding the universe with a hot soup of particles and radiation. This moment, known as reheating, was the true birth of the matter and energy that would go on to form every star, planet, and person. The Big Bang we often speak of is really the aftermath of this inflationary epoch, the moment the Inflaton Field settled down and handed the universe over to the forces and particles we know. This single, hypothetical field was the sculptor of our entire cosmic landscape, setting the stage for everything that was to come. The same Inflaton Field that sculpted our cosmos has a modern counterpart, one that is now tearing it apart. Dark energy is the name for the mysterious force driving the universe's expansion to accelerate, a discovery so shocking it earned a Nobel Prize. Its nature is the most profound puzzle in modern cosmology. Decades before this discovery, Albert Einstein himself had grappled with a similar concept. His theory of general relativity predicted a dynamic universe, one that should either expand or contract. Believing the cosmos to be static and eternal, he introduced a fudge factor into his equations, a repulsive force he called the cosmological constant. He imagined it as a fundamental energy density, an intrinsic property of the vacuum of space itself. When the universe was later observed to be expanding, Einstein discarded the idea as his greatest blunder. Yet he may have been right for the wrong reasons. The modern interpretation of the cosmological constant is that it represents a fundamental field, a uniform energy woven into the very fabric of empty space. This isn't an energy of particles or radiation, but the baseline hum of existence. If the gravitational field is the trampoline sheet, the cosmological constant is like a subtle, repulsive pressure infused within the rubber, causing the entire sheet to stretch itself apart over time. The evidence for this accelerating expansion came from observing distant supernovae. Astronomers used these exploding stars as cosmic mile markers, expecting to see the universe's expansion slowing down due to gravity's pull. Instead, they found the opposite. The most distant supernovae were dimmer than expected, meaning they were farther away than any model of a slowing expansion could account for. Space itself was stretching faster and faster, pushing galaxies apart with an ever-increasing force. But is this dark energy field truly constant, as Einstein first proposed, or is it something more dynamic and strange? Many physicists are not satisfied with a simple constant. They propose alternative fields with names like quintessence. Imagine the cosmological constant as a flat, unchanging plane of energy. Quintessence, by contrast, would be a field that can evolve, a landscape of rolling hills that changes over cosmic time. It could have been stronger in the past, or it could weaken in the future. The ultimate fate of everything hinges on this distinction. If dark energy is a true constant, the acceleration will continue forever. Galaxies outside our local group will be pushed so far away that their light can never reach us, leaving a future sky that is black and empty. If dark energy is a dynamic field like quintessence, its repulsive power could intensify, ultimately overcoming all other forces in a catastrophic big rip, shredding galaxies, stars, planets, and even atoms themselves. Or it could fade away, allowing gravity to once again take command of the cosmos. The true identity of this hidden field, whether constant or evolving, holds the final chapter to our universe's story. While dark energy pushes the cosmos apart on the grandest scale, another hidden field may hold the key to the universe's missing mass. The strong nuclear force, the glue that binds quarks into protons and neutrons inside every atom, presents physicists with a beautiful puzzle. Its governing equations seem to permit a certain kind of asymmetry, an effect that should allow the neutron to possess a tiny, separate electric charge. This would make the neutron act like a minuscule compass needle, a property physicists call an electric dipole moment. Yet, when measured with incredible precision, the neutron shows no such asymmetry. It is perfectly symmetrical. This mismatch between what the math allows and what nature displays is known as the strong CP problem. Why does the strong force seem to respect a symmetry that it is under no obligation to? The most elegant solution is not a tweak to the math, but the introduction of a new cosmic field. In the 1970s, physicists Roberto Pexi and Helen Quinn proposed a solution. They theorized a new field which would give rise to a new particle, the axion. The axion field would act as a cosmic correction fluid. It would dynamically adjust itself across the universe, naturally cancelling out the unwanted asymmetry and forcing the strong force to behave as we observe it, perfectly symmetrical. This fix is so compelling that many believe the axion must exist. The incredible consequence of this solution is the nature of the axion itself. To perform its correcting duty, it must be exceptionally light, potentially billions of times lighter than an electron, and incredibly reluctant to interact with normal matter. It would be a ghost streaming through you and the Earth as if they were not even there. These are precisely the properties that make axions a perfect candidate for the mysterious substance known as dark matter. The invisible axion field permeating all of space could be buzzing with these ultralight particles, their collective gravity shaping the rotation of galaxies and the growth of the cosmic web. The hunt for this ghost is now a major frontier of physics. Experiments like the Axion Dark Matter E-experiment, or ADMX, are listening for the axion's faint signal. They use powerful magnets and supercooled, exquisitely sensitive cavities to try and coax a hidden axion into revealing itself. The magnet would encourage an axion to convert into a faint microwave photon, a single note in the dark waiting to be heard. Finding the axion would be a monumental achievement, solving two of physics' greatest mysteries at once. It would explain the strange symmetry of the strong force and finally identify the invisible matter that holds the cosmos together. The axion is a ghost hiding in plain sight, but some hidden fields are masters of disguise. To explain why we do not feel strange new forces in our daily lives, physicists have proposed a field with a truly bizarre trait. It is called the chameleon field. Just like the reptile that changes its color to match the surroundings, this field changes its very properties based on where it is. Its mass is not fixed. In the emptiness of deep space where matter is sparse, the chameleon field would be very light and have a long range, its influence stretching across vast cosmic distances. This could be the source of the extra gravity we attribute to dark matter, gently sculpting the rotation of galaxies. But here on Earth, surrounded by the dense matter of our planet and the air in this room, the field becomes heavy. Its range shrinks to a microscopic scale, effectively hiding its effects from all our experiments. The field screens itself, blending perfectly into the high-density environment of our world. This clever behavior makes the chameleon a leading candidate in theories of modified gravity, such as MUND, which stands for Modified Newtonian Dynamics. These theories suggest that gravity behaves differently at the extremely low accelerations found in the outer reaches of galaxies, eliminating the need for dark matter. The chameleon field could be the mechanism that makes this work, a single hidden entity that explains the galactic rotation curves without invoking invisible particles. But if the field is so good at hiding, how could we ever hope to find it? Scientists are building exquisitely sensitive laboratory experiments designed to outsmart it. They use ultra-high vacuum chambers, creating a tiny region of near-nothingness inside a dense, shielded apparatus. In this small pocket of low density, the chameleon field should become light and active enough to detect. Researchers then send in a cloud of ultra-cold atoms and watch for any subtle, unexpected pushes or pulls that could only be explained by the field revealing its presence. It is a cosmic game of hide and seek, where we must create a piece of deep space right here on Earth to catch a glimpse of the universe's most elusive field. The same cosmic game of hide and seek applies to a field that could rewrite the very laws of physics. String theory, our most ambitious attempt to unify all forces, introduces a master field called the dilaton. This is not just another field among many, it is the cosmic conductor of the entire orchestra. The dilaton field's value at any point in space dictates the strength of every single interaction in nature. Think of it as a universal dial. When the dilaton field is strong, the force of gravity is strong and the electromagnetic force is strong. When it is weak, all forces weaken in concert. This single underlying field sets the stage for every physical law we observe. Its influence extends even further into realms we cannot see. String theory requires extra spatial dimensions, tiny, curled-up shapes at every point in space. The size of these hidden dimensions is not fixed. It is directly controlled by the value of the dilaton field. A changing dilaton means a changing size for the very fabric of reality's hidden geometry. This leads to a staggering possibility. What if the dilaton field was not always constant? In the violent chaos of the early universe, it could have been dynamic, rolling and evolving. As it changed, so too would the fundamental constants of nature. The speed of light, the strength of gravity, the charge of an electron, all the fixed numbers in our physics textbooks might have been variable in that primordial era. The universe would have been a place of shifting laws, where the rules of physics were not yet set in stone. This idea of a varying dilaton provides a potential solution to one of cosmology's great puzzles, the flatness problem, without needing a period of inflation. A dynamic dilaton field could have naturally driven the universe toward the flat, balanced state we observe today. The dilaton's journey to a stable value would have frozen the constants of nature into the familiar numbers we measure now, locking the dials into place and giving us the stable universe we call home. But what if that lock is not perfect? Could the dilaton field still be shifting today, causing the fine structure constant to change by an infinitesimal amount each year? The hunt for this slow cosmic drift is on, with astronomers analyzing the light from the most distant quasars for any hint that the laws of physics were different in the past. Finding evidence for a dynamical dilaton would be a discovery of unparalleled magnitude, revealing that the laws of nature are not eternal commandments, but the temporary settings of a hidden field, a relic from the universe's first moments. Einstein's smooth spacetime may be missing a crucial ingredient, a hidden twist in the cosmic fabric. General relativity describes a universe where mass and energy curve spacetime, but it treats this fabric as a purely geometric surface, one that can be bent and stretched but not intrinsically twisted. Einstein-Cartan theory introduces this missing twist, a property known as torsion. In this expanded view, spacetime is not merely a flexible sheet, it is more like a complex, pliable gel. Every fundamental particle, like an electron, carries an intrinsic quantum property called spin. Think of this not as a literal ball spinning, but as a fundamental, unchangeable orientation, a tiny arrow of angular momentum. In Einstein-Cartan theory, the concentration of this spin at every point in the universe generates the torsion field, causing the fabric of spacetime itself to writhe and corkscrew on the tiniest scales. This subtle twisting is the hidden partner to the curvature we already know. Where mass tells spacetime how to curve, spin tells it how to twist. This single addition has a profound consequence for the most extreme objects in the cosmos, black holes. In standard general relativity, the immense gravity of a collapsing star crushes all matter into an infinitely dense, infinitely small point called a singularity, a place where the laws of physics completely break down. A torsion-filled universe refuses to accept this infinite breakdown. As matter collapses and spins are packed ever closer together, the resulting torsion field creates an immense repulsive pressure. This pressure fights back against the crush of gravity, preventing matter from ever reaching a point of infinite density. Instead of a singularity, you get a tightly wound, spring-like core of spacetime, a place of immense but finite density often called a Planck star. This could mean that black holes are not eternal prisons, but dynamic objects that might eventually bounce back, releasing their captured energy. For cosmology, this twisting field could have been the dominant force in the universe's first moments. That primordial repulsive pressure generated by torsion looks mathematically identical to the repulsive gravity of the Inflaton Field. It is possible that the universe never needed a separate field to drive its initial explosive growth, that the intrinsic spin of everything within it, twisting spacetime itself, was the true engine of cosmic inflation. This makes the torsion field a powerful bridge, connecting the quantum spin of particles directly to the large-scale structure of the universe, offering a path to finally weave gravity into the quantum tapestry. The twisting geometry of spacetime is not the final layer of reality. To uncover the ultimate nature of the cosmos, we must question the one thing that seems most fundamental: time itself. What if the relentless, forward-flowing river of time is not a primary feature of the universe, but a secondary effect, an illusion emerging from something deeper? A handful of speculative theories propose exactly that, suggesting time is not a background stage but a phenomenon generated by a hidden field, sometimes called the chronon field. In this radical view, the chronon field is the fundamental substrate of temporal experience. Each tick of a clock, each moment of decay, every memory you form could be a localized vibration or a changing value within this field, much like a particle is a ripple in an electron field. Our powerful, undeniable sensation of a past that is fixed and a future that is open may simply be the way our consciousness interprets the complex dynamics of this hidden dimension. This idea forces a direct confrontation with one of physics' great puzzles, the arrow of time. The fundamental laws of physics, for the most part, are time-symmetric. They work just as well if time runs forward or backward, yet our experience is brutally one-directional. We remember the past, not the future. A shattered glass does not spontaneously reassemble. This is the domain of the second law of thermodynamics, which states that the total disorder or entropy of a closed system always increases. The arrow of time points in the direction of increasing chaos. The chronon field could provide the missing link. Perhaps the initial condition of this field at the Big Bang was set in a state of incredibly low entropy, a pristine and highly ordered configuration. As the universe evolved, the dynamics of the chronon field naturally drove it toward higher and higher states of disorder, and our perception of the flow of time is us riding that wave of increasing entropy. The field itself is changing, and we are caught within its current. This leads to one of the most mind-bending concepts in modern physics, a structure that seems to play with time itself, the time crystal. Imagine a perfectly normal crystal like a diamond. Its atoms are arranged in a repeating pattern in space, a symmetry that is broken because the underlying laws of physics are the same everywhere, yet the crystal picks out specific points to place its atoms. A time crystal does something analogous, but in time. In its ground state, its state of lowest energy, it does not sit still. It undergoes periodic motion, returning to its original configuration not in space, but over a regular tick of time. It is a clock that winds itself, forever cycling without consuming any energy. This bizarre behavior challenges our most basic definitions of equilibrium and eternity. It is a structure whose very existence is tied to the periodic ticking of the chronon field, a visible echo of time's underlying granularity. If time is truly emergent from a field, then the distinction between past, present, and future may be as illusory as the solidity of matter. The entire history of the universe could be a single, frozen sculpture within the chronon field, and our journey from birth to death merely a path we are tracing through its static, eternal landscape. This very notion of a frozen, timeless reality finds a strange echo in one of the most radical ideas of modern physics. The holographic principle suggests that our three-dimensional universe, with all its stars, planets, and people, might be a projection from a two-dimensional surface at its edge. Reality could be a cosmic hologram, the information required to describe everything within a volume of space, every event and every particle, is not smeared throughout its interior. Instead, it is painted like a digital code onto the bounding surface of that region. A black hole provides the crucial clue. When matter falls into a black hole, it seems to vanish, destroying information, which violates a fundamental quantum rule. Physicist Jacob Bekenstein calculated that a black hole's entropy, a measure of its hidden information, is proportional not to its volume, but to the surface area of its event horizon. Stephen Hawking later confirmed that black holes do radiate heat and have temperature, cementing the link between gravity, quantum mechanics, and thermodynamics. This led to a staggering realization. The maximum amount of information that any region of space can contain is limited by the area of its boundary, not its volume. It is as if the universe has a pixelated resolution and the pixels live on the surface. This is the heart of the holographic principle. To make this work, physicists propose a fundamental information field underlying everything. In this view, the spacetime we inhabit and the gravity we feel are not the primary reality. They are emergent phenomena, collective behaviors that arise from a vast network of quantum bits or qubits that are entangled on a distant, lower dimensional surface. Imagine the vivid, three-dimensional image projected from a flat, two-dimensional film. The film contains all the information, and the three-dimensional world we see is an illusion generated by that data. In the cosmic version, our entire universe is that projected image. The smooth, continuous fabric of spacetime and the force of gravity are like the convincing image on a high-resolution screen. But if you could zoom in to the Planck scale, you would see the individual pixels, the fundamental units of information from which it is all built. This idea provides a direct, if mind-bending, path to a theory of quantum gravity. In the holographic description, gravity is no longer a fundamental force. It is an entropic force, a statistical effect that emerges from the system's tendency to maximize its disorder, much like the pressure in a gas emerges from the chaotic motion of countless molecules. The pull you feel towards the Earth would be a consequence of the way information is structured and evolving on the universe's hidden boundary. The holographic principle transforms our deepest questions. We no longer ask what spacetime is made of, but how it is computed. The cosmos is not a place, but a process, a dynamic calculation happening on the ultimate screen, and we are living inside its projection. This hidden architecture of the cosmos is built upon a principle of perfect balance. Symmetry is the fundamental beauty underlying the laws of physics, the idea that a system remains unchanged even when you rotate it, reflect it, or shift it in space or time. Yet our universe is a place of obvious imbalance, filled with distinct particles of different masses and forces of varying strengths. This great paradox is resolved by one of the most powerful ideas in all of physics: spontaneous symmetry breaking. Imagine a perfectly sharp pencil balanced on its tip. The system is completely symmetrical. Every direction away from the tip is identical, but this state is unstable. The pencil must fall, and when it does, it picks one specific, random direction. The perfect symmetry of the possible states is broken by the actual, single state the system chooses. This is the essence of spontaneous symmetry breaking. In field theory, this is visualized with a potential energy landscape shaped like a Mexican hat or a sombrero. The high point in the very center is symmetrical but unstable, like the pencil on its tip. The stable states are not at the top, but in the trough of the brim, where the field can rest at a lower energy. To get there, the field must pick a direction and roll down, breaking the symmetry of the circular brim by settling into one specific, random point. The Higgs mechanism is the most famous example of this. The Higgs field exists in that symmetrical but unstable high-energy state. As the early universe cooled, it underwent a phase transition. The Higgs field tumbled down into the stable trough, picking a specific value everywhere in space. This act of choosing one value is what broke the symmetry of the electroweak force, splitting it into the two distinct forces we see today: the electromagnetic force and the weak nuclear force. The particles that interact with the Higgs field, like the W and Z bosons, suddenly found themselves wading through this new cosmic molasses, acquiring mass in the process. This was not a one-time event in the early cosmos. Spontaneous symmetry breaking is the engine behind every phase transition, from water freezing into ice to a magnet forming. In a hot piece of iron, the atomic spins are pointing in random directions, a symmetrical and disordered state. As the metal cools, the spins spontaneously align in one particular direction, breaking the rotational symmetry and creating a macroscopic magnetic field with a definite north and south pole. In the universe's first moments, a series of such cosmic phase transitions may have occurred as various fields settled into their stable states, each event carving the distinct forces and particles we now observe from a primordial state of perfect, featureless symmetry. The universe we inhabit is not one of perfect balance, but one that chose to be lopsided, and that very lopsidedness is what allowed for the rich complexity of stars, planets, and life to emerge. But what if the force tearing the cosmos apart is slowly changing its mind? The cosmological constant presents a simple, static picture of dark energy, a steady pressure woven into the vacuum of space. Yet many physicists suspect the truth is far more dynamic, governed by a field that evolves across the eons. This is the theory of quintessence, a name hearkening back to the ancient Aristotelian fifth element, the pure substance of the heavenly realms. In this modern vision, quintessence is a scalar field, a single number assigned to every point in space, and that number is not fixed. It can roll and shift across a vast cosmic landscape, its energy density changing as it moves. This subtle evolution makes all the difference for the fate of everything. Imagine two futures. In one, governed by a true cosmological constant, the acceleration of the universe's expansion continues at its current steady pace. Billions of years from now, our local group of galaxies will be an isolated island in an ever-darkening, ever-expanding void. In the other future, dictated by quintessence, the outcome is uncertain. The field could be slowly weakening, a phenomenon called fading quintessence. If this happens, the repulsive force of dark energy might one day diminish, allowing gravity's pull to reassert its dominance. The universe could eventually stop accelerating, perhaps even begin to contract, leading to a potential big crunch. Conversely, the field could be growing stronger, a scenario known as phantom dark energy. This would lead to a far more violent end, the Big Rip. In this cataclysm, the accelerating expansion does not just push galaxies apart, it becomes so powerful that it overcomes the very forces holding matter together. First, galaxy clusters would be torn asunder, then galaxies themselves would be shredded. As the end approaches, the phantom field's repulsion would rip stars from their solar systems, planets from their stars, and finally, overcome the nuclear and electromagnetic forces binding atoms and molecules. In the last instance, every atomic nucleus, every proton and neutron would be violently pulled apart. The universe would end not with a collapse, but with a silent, cosmic disintegration into its most fundamental, disconnected particles. The monumental challenge for astronomers is distinguishing between these futures. A constant field and a slowly evolving quintessence field produce nearly identical effects over the short, cosmic timescale of our observations. It is like trying to measure if a mountain is growing by watching it for a single second. The tiny, cumulative changes in the expansion rate over billions of years are what would reveal the field's true nature. This requires measuring the distances to supremely faint, ancient supernova with exquisite precision, a task for the next generation of space telescopes. Discovering that dark energy is quintessence would be a revolution. It would mean the vacuum of space is not a static stage but a dynamic, breathing entity. The force shaping the cosmos's ultimate destiny would be a living field, one whose story is still being written, and its final chapter remains a secret hidden in the deep, dark sky. The smooth, geometric curves of spacetime in general relativity hide a frantic quantum secret. To truly unite gravity with the other forces, we must find its particle, the graviton. Just as the photon is the messenger particle for the electromagnetic force, the graviton would be the quantum carrier of gravity, a tiny ripple in a fundamental graviton field. This field would underlie the spacetime fabric, and its vibrations would transmit the force of gravity from one mass to another, painting Einstein's elegant curvature with the brushstrokes of quantum mechanics. The challenge in finding this particle lies in gravity's profound weakness. Gravity is so incredibly faint that the gravitational pull between two protons is a trillion times weaker than their electromagnetic repulsion. To detect a single graviton, you would need an experiment of almost ludicrous scale, perhaps a detector the mass of Jupiter placed in close orbit around a neutron star, and even then, the signal would be almost indistinguishable from the quantum noise of the universe. This weakness is also why gravitons barely interact with each other, making the gravitational field far simpler in some ways than the messy quantum fields that govern other forces. Yet, the properties of this elusive field and its particle are the cornerstones of our most ambitious theories of everything. In string theory, the graviton emerges naturally as a specific pattern of vibration of the fundamental strings, a closed loop whose oscillation perfectly matches the expected properties of the gravity carrier. In loop quantum gravity, spacetime itself is quantized, woven from a network of finite loops, and the graviton would be an excitation of this woven fabric, a defect in the spin network that propagates through it. Discovering the graviton would be the final, monumental piece of the unification puzzle. It would prove beyond any doubt that gravity is a quantum force at heart, forcing a complete rewrite of our understanding of reality's most fundamental layer. It would bridge the colossal gap between the immense and the infinitesimal, revealing a single, coherent set of laws governing everything from the fall of an apple to the birth of a galaxy. Until we can capture this ghostly ripple, the dream of a final theory remains just out of reach, a silent whisper in the quantum static of the cosmos. The phantom energy field is a dark energy so potent it could unravel reality itself. This is not a gradual drifting apart, but a future of absolute, violent disintegration. While the cosmological constant and quintessence push galaxies away, their influence is limited. Phantom energy possesses a far more sinister property, a negative pressure so extreme that its energy density actually increases as the universe expands. Think of it as an anti-gravity that feeds on itself, growing stronger and more ravenous as space stretches. The acceleration would not just continue, it would skyrocket exponentially. The timeline for this cosmic demolition is shockingly finite. First, the phantom field's strengthening grip would overcome the gravitational glue holding our local supercluster together. Galaxies would be flung into the deepening void. Then, the Milky Way itself would be torn apart, its stars scattered like dust in a hurricane. As the end draws near, our solar system would be shredded. The phantom energy's repulsive force would exceed the Sun's gravity, and Earth would be ripped from its orbit. In the final minutes, the force would overcome the very bonds holding our planet together. Mountains would fly apart, the ground would vaporize, and finally, the phantom field would target the building blocks of matter itself. It would tear electrons from their atomic orbits and rip apart atomic nuclei, severing the strong nuclear force that even a black hole's gravity cannot break. The universe would end not with a collapse or a freeze, but with a silent, ultimate dissolution into a thin, cold soup of disconnected fundamental particles, forever flying apart. The theoretical problem with this apocalyptic vision is a profound one. For phantom energy to exist, it must violate certain energy conditions that physicists believe are fundamental to a stable universe. It ventures into territory where matter can have negative energy density, leading to bizarre possibilities like wormholes and time travel, and potentially rendering the vacuum of space unstable. The question of its physical viability remains one of cosmology's most intense debates, a terrifying possibility hanging over our understanding of cosmic fate, a final scream from a hidden field pushed to its absolute limit. Our elegant Higgs mechanism might not be the only way to give mass to the universe. Another compelling idea suggests we have been looking at the problem from the wrong angle entirely. This is the theory of Technicolor, which proposes a radical alternative to the fundamental Higgs field. Imagine the force that binds quarks together into protons and neutrons, the strong nuclear force. It is incredibly powerful, and it works through a kind of cosmic glue made of particles called gluons. Technicolor theory postulates a whole new, similar force, a Technicolor force, complete with its own technogluons and a new family of fundamental particles called technifermions. In this picture, there is no fundamental Higgs field permeating space. Instead, the mass-giving mechanism is a dynamic process, a side effect of this powerful new interaction. At extremely high energies, these technifermions would be massless and free, much like quarks are at high energies. But as the universe cooled, the Technicolor force would become strong, causing the technifermions to bind together into composite particles. One of these composite particles would look and act exactly like the Higgs boson we discovered. In this scenario, the Higgs is not an elementary particle, but a bound state, a kind of technihadron, much like a proton is a bound state of quarks. The cosmic molasses that gives other particles their mass is not a fundamental field, but emerges from the frantic interactions of these more basic technic constituents. This was a beautiful and self-contained idea, offering a way to generate mass without introducing a fundamental scalar field, which many physicists found aesthetically displeasing. However, the discovery of the Higgs boson in 2012 presented a serious challenge. The particle found at the Large Hadron Collider had a mass of about 125 billion electron volts, and its properties, its spin, and how it interacted with other particles matched the predictions of the simple, fundamental Higgs of the Standard Model almost perfectly. Technicolor models, in their original form, tended to predict a much richer spectrum of new, heavy particles and significant deviations from what was observed. The data simply did not show these expected companions. Consequently, basic Technicolor theories fell out of favor, yet their legacy is far from dead. The core concept of dynamical symmetry breaking, of mass emerging from a strong force, remains a powerful and inspiring principle in physics. It has seeded the development of more sophisticated models like composite Higgs theories, where the Higgs is still a composite particle, but its properties are tweaked to align with what we see. The spirit of Technicolor lives on in the ongoing search for what lies beyond the standard model, a reminder that the Higgs we found might just be the first glimpse of a much deeper, more complex structure. The search for a deeper symmetry leads us to one of the most elegant ideas in theoretical physics. Supersymmetry proposes a breathtakingly simple relationship at the heart of reality, a fundamental partnership between the two great families of particles. On one side are the fermions, the building blocks of matter like electrons and quarks. On the other are the bosons, the force carriers like photons and gluons. Supersymmetry declares that this division is not absolute. It postulates a new set of hidden fields, the supersymmetric fields, which weave this cosmic divide together. For every known fermion, there must be a bosonic superpartner. For every known boson, there must be a fermionic superpartner. The electron, a fermion, would be paired with a selectron, a boson. The photon, a boson, would be paired with a photino, a fermion. This elegant doubling of the cosmic roster is not just for aesthetic appeal, it solves some of the most nagging problems in physics. The most pressing is the hierarchy problem, a question of unnatural fragility. The mass of the Higgs boson is incredibly sensitive to quantum corrections from all other particles. In the standard model, the wildly different energy scales between the weak force and gravity should drive the Higgs mass to an astronomically high value, making our universe impossible. But in a supersymmetric universe, every particle's superpartner contributes an opposing correction. The electron's effect is cancelled by the selectron, the photons by the photino. This delicate cancellation naturally protects the Higgs mass, keeping it at the low, stable value we observe. This beautiful fix has a staggering consequence. The lightest of these superpartners, often thought to be the neutralino, would be stable, electrically neutral, and only interact weakly with normal matter. These are precisely the properties required for a dark matter particle. Supersymmetry could therefore solve two profound mysteries with a single, elegant stroke, explaining both the stability of the Higgs field and the identity of the invisible matter that shapes the cosmos. Furthermore, this new symmetry forces the three fundamental forces of the standard model, the electromagnetic, weak, and strong forces, to unify into a single grand force at extremely high energies. Their strength, which today are very different, are projected to converge at one specific energy scale in a supersymmetric universe, a powerful hint that we are on the right track. Yet, for all its mathematical beauty, nature has so far refused to reveal these superpartners. Not a single selectron or photino has been seen in our most powerful colliders. This forces a difficult question. Is supersymmetry a broken symmetry, its partners so heavy they lie just beyond our current reach, or is the universe simply less symmetrical than we had hoped? The silence of the detectors is a profound puzzle, a beautiful idea waiting for the cosmos to prove it right. The elegant symmetries of physics propose a hidden order, but what if nature remembers its own habits? A deeply controversial idea from biologist Rupert Sheldrake suggests that the formative principles of life are not just in our genes, but in invisible fields of memory. He calls these morphic fields, and they are said to govern the development and behavior of everything from a single cell to an entire species. According to this theory, a morphic field contains a collective memory, built up by the past forms and actions of all previous members of that species. This memory is then accessed through a process called morphic resonance, where an individual organism tunes into the habits of its kind across both space and time. A classic example is a laboratory experiment where rats in one location learn a new maze. If morphic resonance is real, rats of the same breed in a different lab anywhere in the world should then learn that same maze more quickly, simply because the knowledge has entered the species' collective field. This would not involve any known form of energy transmission, but a resonance with a pattern that transcends physical location. Sheldrake extends this idea beyond biology, proposing that even crystals and molecules have morphic fields. The reason a chemical compound consistently forms the same crystal structure, he argues, is not just due to immutable physical laws, but because it has crystallized that way billions of times before, and the pattern has become a habit reinforced by morphic resonance. This is where the theory collides violently with mainstream science. Critics argue that morphic fields lack any plausible physical mechanism. They ask what carries this information, how it is stored, and how resonance could possibly work without any known energy or force. The central accusation is that the theory is not falsifiable, that failed experiments can be explained away by suggesting the field was not strong enough or the conditions were not right. For the vast majority of biologists and physicists, this places morphic resonance firmly in the realm of pseudoscience, an untestable idea that explains everything and therefore nothing. Yet, despite this rejection, the concept has found a powerful resonance of its own within alternative science circles and holistic communities. It offers an appealing narrative of interconnectedness, a universe that learns and evolves, where instinct is not a blind genetic program but a living memory. It challenges the reductionist view that all of life can be explained by chemistry and physics alone, proposing instead that habit and history are active, formative forces in nature. The debate itself highlights a fundamental tension in our quest for knowledge, a struggle between the comfort of established mechanisms and the allure of radical, if unproven, possibilities. Even the emptiest void in the universe is not truly empty. Beneath the level of atoms, beneath even the concept of particles, lies a seething, vibrant sea of energy known as the zero-point field. This is the lowest possible energy state a quantum field can have, but it is a state of restless activity, not peaceful silence. The Heisenberg uncertainty principle forbids any particle or field from ever being completely still. If it were, we would know its exact position and momentum, which the quantum rules of our universe do not allow. So every point in space hums with a fundamental, irreducible energy. This quantum jitter is the engine behind one of the strangest phenomena in physics, the spontaneous creation of virtual particles. Pairs of particles and their antiparticles can borrow energy from the zero-point field, popping into existence for an immeasurably short moment before annihilating each other and returning the energy. It is a constant, frantic dance of creation and destruction happening all around you, in the space between your hands and in the air you breathe. This is not just a mathematical curiosity, it has real, measurable consequences. Bring two perfectly smooth, uncharged metal plates extremely close together in a vacuum, separated by a tiny gap. This is the setup for the Casimir effect. The space between the plates is so narrow that only virtual particles with certain wavelengths can flicker into existence there. Outside the plates, a much wider sea of virtual particles of all wavelengths can form. The greater pressure from the particles outside pushes the plates together with a faint but detectable force. The invisible energy of the vacuum has produced a real physical push. Another proven effect is the Lamb shift, a tiny change in the energy levels of the electron in a hydrogen atom. This slight shift, a crucial confirmation of quantum electrodynamics, is caused by the electron constantly interacting with the virtual particles bubbling up from the zero-point field, jostling it ever so slightly from its predicted orbit. Yet this confirmed reality leads to one of the most profound embarrassments in all of theoretical physics. If we can observe these local effects, we should be able to calculate the total energy density of this quantum vacuum. When physicists perform this calculation, summing up the contributions from all possible quantum fields, the result is a number so catastrophically large it defies comprehension. The theoretical energy of empty space should be around 120 orders of magnitude greater than what we observe. To put that in perspective, it is the difference between the energy in a single drop of water and the energy in all the oceans on Earth. This vacuum energy, according to general relativity, should produce a colossal gravitational repulsion. A universe with that much vacuum energy would have blown itself apart in the first instant of the Big Bang, ensuring that no stars, planets, or life could ever form. But our universe exists, and its expansion is accelerating at a very gentle, measured pace. The observed value of dark energy, the force driving this acceleration, is almost zero when compared to the theoretical prediction. This staggering mismatch between the quantum calculation and the cosmic observation is the cosmological constant problem. Why is the energy of the vacuum so much smaller than it should be? Why is it not zero, but just this tiny, specific value that allows for galaxies and life to emerge? Some physicists propose a delicate, perfect cancellation, where positive and negative contributions from different fields somehow balance out to nearly zero through a mechanism we do not yet understand. Others wonder if the vacuum energy is not a true constant at all, but has dynamically relaxed to its current value, a puzzle that connects back to fields like the dilaton. This colossal error is not a minor oversight. It is a fundamental warning that our understanding of the quantum vacuum and its relationship to gravity is deeply incomplete, a silent scream from the void that our two most powerful theories of reality are still at war. The vacuum energy catastrophe exposes a deep fracture in our understanding of reality. For decades, the greatest minds in physics have pursued a single framework that could heal this divide, a master theory that would weave all of nature's forces and particles into one seamless tapestry. This is the dream of a unified field theory, a single equation from which the entire cosmos could be derived. Albert Einstein spent the last 30 years of his life on this quest, relentlessly searching for a way to unite his theory of gravity with Maxwell's theory of electromagnetism. He envisioned a purely geometric universe where particles were not separate entities but tiny knots in the fabric of spacetime itself. He worked in isolation, guided by a powerful intuition that the universe must ultimately be simple and beautiful. Yet, the mathematical tools of his time were not equal to the task, and the quantum revolution revealed a world far more chaotic and probabilistic than his classical mind could accept. His lonely quest ended without success, but the torch was passed. Today, the most promising candidate for this final theory is string theory. It makes a breathtakingly simple proposition that the fundamental constituents of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy. These strings are so small that if an atom were enlarged to the size of our solar system, a string would be no larger than a tree on Earth. The different vibrations of a single string are what create the entire zoo of particles. One specific resonance pattern gives you an electron, another produces a quark, and yet another manifests as the photon or the graviton. In this elegant picture, every particle and every force carrier is just a different note played on the same fundamental instrument. The force of gravity and the laws of quantum mechanics are no longer at war because they both emerge from the same underlying vibrational reality. But this beautiful simplicity comes at a staggering cost, extra dimensions of space. For the mathematics of string theory to work consistently, it requires not just the 3 spatial dimensions we experience, but 6 or 7 additional ones, curled up into shapes so tiny we never notice them. Every point in our familiar 3-dimensional space hides an entire miniature universe of complex geometry. This evolved into M-theory, a broader framework that unites the various competing string theories. M-theory introduces a new fundamental object, the membrane, or brain for short. These can have multiple dimensions, like 2-dimensional sheets or higher dimensional solids. In this vision, our entire universe could be a 3-dimensional brain floating in a higher dimensional bulk, and the particles we see might be strings attached to our brain, while gravity alone could leak across the dimensions. The mathematical beauty of this framework is profound, but it is also its greatest weakness. The theory is so flexible, with a near infinite number of possible solutions for how the extra dimensions could be curled up, that it can predict almost anything. This vast landscape of possibilities makes it incredibly difficult to extract a single, testable prediction that could be verified in a laboratory. We are left with a theory of breathtaking scope and elegance, a potential key to the universe's deepest secrets, yet one that remains, for now, suspended in a realm of pure mathematical speculation, waiting for a single, concrete piece of evidence to tether it to our reality. The profound imbalance of our universe is written into every atom of our bodies. We live in a cosmos made almost entirely of matter, but the laws of physics, as we understand them, treat matter and antimatter as perfect equals. For every particle created in the Big Bang, an antiparticle should have been its mirror twin. When matter and antimatter meet, they annihilate in a flash of pure energy. So why did all the antimatter vanish, leaving behind just enough matter to build every galaxy and star? This is the puzzle of baryon asymmetry, and one of the most elegant solutions lies in the oscillations of a hidden field. Proposed by physicists Ian Uffolk and Michael Dine, this mechanism involves a special kind of scalar field, a cousin to the Higgs but with a unique purpose. In the universe's first chaotic moments, this field was displaced from its lowest energy state, perched on an uneven slope of its potential. As the cosmos cooled, the field began to roll down this slope, but it didn't roll straight. It oscillated like a ball rolling back and forth in a bowl, and with each swing, it generated more matter than antimatter. This was not a random accident. The field was designed to couple differently to particles and their antiparticles, effectively giving matter a slight preferential treatment during its energetic wobbles. These oscillations acted like a cosmic pump, flooding the young universe with a vast excess of quarks over antiquarks. For every billion annihilations that returned to energy, a single quark was left over, spared from destruction by the field's asymmetric push. That 1 in a billion survivor is the reason you exist. Every proton, every neutron in every atom is a descendant of that tiny surplus, the indelible signature of a field that tipped the first and most important scales. Without this hidden dynamic, matter and antimatter would have completely wiped each other out, leaving a universe of featureless light, empty of structure and utterly devoid of life. Deep in the cold expanse beyond Jupiter, 2 robotic explorers began to drift off course. The Pioneer 10 and 11 spacecraft, after their triumphant flybys of the gas giants, were on their way out of the solar system. Yet as scientists tracked their trajectories, they noticed something deeply puzzling. Both probes were experiencing a tiny, unaccountable deceleration, a constant, faint tug back toward the sun. This was the Pioneer anomaly, a drift so small it amounted to less than a billionth of the gravity we feel on Earth, but it was there and it defied every conventional explanation. For years, this ghostly pull fueled speculation about hidden forces at play. Perhaps it was evidence of a new, long-range field interacting with the spacecraft, a subtle modification to the laws of gravity itself that only became noticeable in the vast, quiet stretches of interplanetary space. Maybe Einstein's theory needed a slight adjustment, and this anomaly was the first whisper of a deeper truth. The mystery was a perfect catalyst for theoretical creativity, pushing physicists to propose novel fields that could tweak gravity on cosmic scales. The ultimate resolution, however, was not a new force but a very old one, understood in a new light. Meticulous analysis eventually pinpointed the culprit: thermal radiation pressure. The radioactive decay from the probe's power sources generated heat, and that heat radiated away from the spacecraft in the form of photons. Every photon carried a tiny amount of momentum, and as they were emitted preferentially from the warm, aft-facing side of the probes, they created a gentle but constant pushback toward the sun, exactly mimicking a gravitational drag. The anomaly was not a flaw in our laws of physics, but a testament to their relentless, comprehensive power, even over effects we initially overlook. Yet the legacy of the pioneer anomaly endures as a powerful lesson. Such cosmic whispers, even when they turn out to have mundane explanations, are the very events that drive science forward. They force us to question our assumptions and to propose bold new ideas like hidden fields or modified gravity that might one day explain the next real mystery we encounter. This cycle of mystery, proposal, and rigorous testing is how we peel back the layers of the cosmos, always listening for the next faint signal in the silence. The universe's first light holds a secret message from its birth. This light is the cosmic microwave background, a faint afterglow from the hot, dense plasma that filled the cosmos just 380,000 years after the Big Bang. For the most part, this ancient radiation is incredibly uniform, a near-perfect thermal blanket stretched across the sky. But when scientists built exquisitely sensitive maps of this background, they found strange, large-scale blemishes that refused to fit our standard models. One of the most puzzling is nicknamed the axis of evil. It is not a physical axis, but a mysterious alignment in the temperature fluctuations of the CMB. The hot and cold spots seem to line up in a particular direction across the sky, a preferred orientation that should not exist in a perfectly random, isotropic universe. It is as if the cosmic dice were loaded from the very beginning. Another profound mystery is the cold spot, a vast, unusually cool region in the southern sky. It is so large and so cold that it is incredibly unlikely to have formed by random chance in our standard cosmological model. It looks like a cosmic bruise, a place where something monumental happened. These anomalies suggest that the universe on its largest scales is not quite as we expected. To explain them, physicists are turning to exotic fields that were active in the universe's first moments. Perhaps the Inflaton Field, the driver of cosmic inflation, was not perfectly uniform. It could have had a slight directional preference, an imperfection that twisted the fabric of spacetime as it expanded, imprinting that preferred direction onto the CMB as the axis of evil. Or the cold spot might be the signature of a cosmic defect. As another early universe field settled into its stable state, it could have created a massive texture, a kink in the fabric of spacetime. The energy released when this texture unwound itself would have left a vast, cold shadow on the first light, a scar we can still see today. Another possibility involves a collision with another universe in the multiverse. If our cosmos exists on a giant membrane or brain floating in a higher dimensional bulk, it could have gently bumped into a neighboring brain. That collision would have deposited a tremendous amount of energy in one specific region of our sky, creating the cold spot as a cosmic echo of that long-ago encounter. These are not just wild speculations, they are testable hypotheses. The next generation of CMB experiments, like the Simons Observatory and the Lightbird satellite, are being built with unprecedented sensitivity. They will scan the sky, measuring the polarization of this ancient light with microscopic precision. The pattern of that polarization is a direct fossil record of the primordial fields that shook the universe during inflation. If an exotic field was truly responsible for these anomalies, its unique signature will be written in the polarization data. Finding it would be like reading a diary from the first trillionth of a second of time, revealing new physics from the absolute dawn of existence. A spacecraft engine that needs no fuel sounds like pure science fiction. Yet for years, a small, controversial device known as the EM drive sparked exactly that possibility. Its design was bizarrely simple, a metallic cone-shaped cavity that you pump full of microwaves. According to the law of conservation of momentum, for a rocket to move forward, it must throw something backward. The EM drive appeared to do the impossible. It seemed to produce a tiny, persistent thrust while expelling absolutely nothing. If real, it promised to revolutionize space travel, powering us to Mars in weeks and to the stars within a human lifetime. The apparent violation of a bedrock law of physics meant one of two things. Either we had witnessed a monumental experimental error, or we were seeing the shadow of a new, hidden field at work. Proponents of the latter idea reached for a radical explanation rooted in the quantum vacuum. They proposed that the engine was not pushing against nothing, but against the seething sea of virtual particles that make up the zero-point field. In this view, the quantum vacuum is not a true void, but a kind of virtual plasma, a medium dense with particle-antiparticle pairs flickering in and out of existence. The theory suggested that the resonant microwaves inside the EM drive's chamber could interact with this plasma, exchanging momentum with it. The drive would, in effect, be pushing off against the fabric of spacetime itself, using the quantum foam as its propellant. This is a deeply speculative idea, and most physicists remain profoundly skeptical. The quantum vacuum, for all its strange activity, cannot be used as a propellant in this way. Virtual particles are not real particles you can push against. They are transient manifestations of a field's uncertainty. Pushing against them would be like trying to push against a shadow. Every careful analysis points back to experimental error, subtle thermal effects, or magnetic interactions with the Earth's field that mimic a thrust signal. Despite the almost certain mundane explanation, the EM drive story is not a failure. It represents a vital, if controversial, pressure point on the boundaries of field theory. It forces us to ask profound questions about the nature of the vacuum and whether our understanding of momentum conservation is complete in all contexts. It is a testament to our enduring desire to find a loophole in the cosmos, a clever way to tap into the hidden energy of empty space and sail on the quantum winds. The same quantum static that fills the vacuum might also hold the spark of awareness. At the farthest edge of physics and philosophy lies a theory that challenges our most basic assumption about reality, panpsychism. This idea proposes that consciousness is not a rare and recent product of complex brains, but a fundamental and ubiquitous feature of the cosmos, as basic as space and time. In this view, the capacity for some form of experience is present in all things, from a human being to an electron. This is not to say a rock is thoughtful or a river is sad, but that the most rudimentary precursor of feeling, a faint glimmer of subjective experience, might be woven into the fabric of existence itself. If this is true, then a universal consciousness field could permeate reality, a hidden dimension where the inner life of the universe resides. This radical idea finds a strange echo in one of the most debated aspects of quantum mechanics, the observer effect. In the famous double-slit experiment, particles like electrons behave as waves when not observed, creating an interference pattern. But the moment a measuring device is used to determine which path the electron takes, the wave-like behavior vanishes and the electron acts like a single particle. The mathematics describes this as the collapse of the wave function, but what exactly triggers this collapse? The standard interpretation places the observer outside the system, but some speculative theories suggest the observer's consciousness itself is the key ingredient. Perhaps a universal consciousness field is what resolves quantum uncertainty, collapsing probability into definite reality through the act of observation. This provides a potential, though highly controversial, solution to the hard problem of consciousness, which asks why and how physical processes in the brain give rise to subjective experience. How does the firing of neurons create the redness of red or the feeling of pain? If consciousness is fundamental, then it does not emerge, it is already there, and complex systems like our brains are simply exceptionally good at amplifying and structuring it. The scientific skepticism towards these ideas is profound and warranted. They are nearly impossible to test with our current methods, and they risk venturing into the realm of metaphysics rather than empirical science. Critics argue that attributing consciousness to particles is a category error, a confusion of levels of description. Yet, the appeal of panpsychism endures because it offers a way to place consciousness within a naturalistic world, without dismissing its reality. It suggests that we are not strangers in a dead universe, but expressions of a cosmos that is, in some deep and fundamental way, awake. A particle that forever outruns its own light would rewrite the laws of cause and effect. This is the strange promise of the tachyon, a hypothetical entity born from a field with a property so bizarre it is described as an imaginary mass. In our everyday world, adding energy to an object makes it move faster. For a tachyon, the rules are inverted. Its imaginary mass means that adding energy actually slows it down, pushing it closer and closer to the speed of light from above, a barrier it can never drop below. The most mind-bending consequences emerge when we view these particles through the lens of Einstein's relativity. From certain perspectives, a tachyon traveling faster than light would appear to be moving backwards in time. Its effect would be seen before its cause, a clear violation of the logical sequence that structures our reality. Imagine a signal sent via tachyon, where the reply arrives before the original message is even sent. This paradox is the primary reason most physicists relegate tachyons to the realm of mathematical curiosities, artifacts of equations that do not correspond to anything in our physical universe. They represent a fundamental instability, a sign that a theory is not quite right. Yet, these phantoms have not been completely banished. In the complex landscapes of string theory, tachyons occasionally appear in the equations describing certain states of strings, particularly those associated with unstable configurations like decaying D-branes. Their presence is a red flag, indicating an unstable vacuum state that must decay into a more stable, lower-energy configuration, a process that banishes the tachyon from the final physical theory. So while we will likely never detect a tachyon streaking through a laboratory, its ghostly presence in our mathematics serves a vital purpose, guiding theorists away from unstable dead ends and toward a more complete picture of the cosmos. Einstein's smooth spacetime geometry dissolves into chaos at its very foundation. Beneath the level of atoms, beneath even the quantum fields, lies a seething, turbulent ocean known as quantum foam. This was the visionary idea of physicist John Archibald Wheeler, who proposed that the gravitational field, when viewed at the unimaginably small Planck scale, is not a placid continuum. Instead, it is a frothing, bubbling sea of virtual wormholes and fluctuating geometry. At this scale, the very concepts of before and after, or here and there, lose all meaning. The fabric of reality is in a state of constant, violent reinvention. Wormholes blink in and out of existence, connecting distant points for a fleeting instant before vanishing. Tiny regions of space curl up into multiple dimensions, only to smooth out again a moment later. This is the ultimate nature of a dynamic gravitational field when quantum mechanics takes full command. It is a foam, a churning ocean of potential where the geometry of spacetime itself is subject to the same uncertainty that governs particles. This radical vision has profound implications for the unification of gravity and quantum mechanics. It suggests that the smooth, curved spacetime of general relativity is not fundamental, but an average, a large-scale illusion that emerges from this frantic, microscopic turbulence, much like the smooth surface of a pond emerges from the chaotic motion of countless water molecules. If Wheeler was correct, then the stage upon which the universe plays out is not a static set, but a living, breathing entity, constantly remaking itself from moment to moment in a storm of geometric creativity. A concept once banished from physics now whispers from the shadows of our most advanced theories. The luminiferous ether was the great phantom of 19th century science, an invisible, frictionless medium that physicists believed must fill all of space. Light was understood to be a wave, and every wave needs something to wave in. Sound needs air, ocean waves need water, so light, it was reasoned, must need the ether. This hypothetical substance was the stage upon which the cosmic drama of light played out, an absolute frame of reference for the universe. Then came the experiment that shattered this elegant idea. Albert Michelson and Edward Morley designed an exquisitely sensitive instrument to detect the ether wind. As Earth moved through this stationary medium, they reasoned, it should create a detectable drift, just as a boat moving through water creates a current. They split a beam of light, sent the parts on perpendicular journeys, and brought them back together to look for an interference pattern that would shift as the apparatus turned. The result was a stunning nothing. There was no shift, no drift, no sign of the ether at all. The universe was silent. This null result was a crisis in physics, a foundation stone that had simply vanished. A young Albert Einstein would resolve the crisis by dismantling the entire stage. His theory of special relativity declared that there is no absolute rest frame. The speed of light is constant for all observers, regardless of their own motion. The ether was not merely undetected, it was unnecessary, a superfluous ghost exercised by a new, more powerful logic. The concept was declared dead and buried. Yet, ideas in physics have a curious habit of resurrection. The ether was wrong in its original form, but its core intuition that space is not a true void has returned with a vengeance. We now know that the vacuum is not empty. It is filled with the Higgs field, a cosmic molasses that gives particles mass. It is alive with the quantum foam, a seething ocean of virtual particles. It possesses a baseline energy density, the cosmological constant. These are not stationary, mechanical media like the old ether, but dynamic quantum fields that are part of the very definition of space itself. In a profound twist, our modern understanding has not restored the ether, but has instead revealed that space itself has properties, structure, and energy. The old ether was a thing in space. The new ether is space, or rather, it is the collection of fundamental fields whose excited states we call particles and whose ground state we call the vacuum. The ghost of the ether lives on not as a substance but as a principle that the void is full and that the emptiness between the stars is the most active place of all. A faint, almost imperceptible light seems to glow within every living cell. Scientists have measured these ultra-weak emissions, calling them biophotons. While the light is incredibly dim, thousands of times fainter than normal bioluminescence, its very existence has sparked a profound debate about the nature of life itself. Mainstream biology explains these biophotons as a simple byproduct of the body's routine chemistry. Our cells are constantly engaged in metabolic processes, many of which involve oxidative stress. This is a kind of cellular rust where reactive molecules can damage tissues. As a side effect of this damage and the subsequent repair, molecules can become excited and release their excess energy as a photon of light. In this view, biophotons are just the exhaust fumes of a busy cellular engine, a passive glow with no deeper meaning. But other researchers propose a far more radical interpretation. They suggest these tiny light emissions are not just random waste, but part of a coherent communication network, a hidden life field that helps to coordinate and organize biological processes. This hypothetical biofield would act as an information blueprint, using light to synchronize everything from cell division to tissue repair. Imagine a city at night, its countless lights twinkling. From a distance, it looks like a chaotic mess, but in reality, each light is part of a coordinated system, with traffic signals and communication networks guiding the flow of life below. Proponents of the life field theory suggest our bodies operate in a similar way, with biophotons serving as the traffic signals for cellular activity, directing healing and maintaining order. Some experiments even show that damaged cells can stimulate healthy neighbors to increase their light emissions, as if calling for help across a photonic network. The scientific evidence for this organized field remains highly controversial. while we can measure the light, proving it carries meaningful information rather than just reflecting random chemistry is the monumental challenge. For now, the idea of a life field resides at the frontier of science, a beautiful and compelling hypothesis that walks the line between measurable fact and biological mystery. It asks a fundamental question: is life merely an intricate chemical machine, or is it something more, orchestrated by a hidden light we are only just beginning to see? Our own universe's specific laws and constants might be nothing more than a cosmic accident. This final theory takes the idea of hidden fields to its ultimate conclusion, the concept of the multiverse. In particular, string theory gives us a staggering vision known as the landscape. This is not a physical place of mountains and valleys, but an abstract terrain of possibilities for the universe's fundamental fields. Each of the scalar fields we have discussed, from the Higgs to the Inflaton, has a potential energy landscape, a map of all the stable and unstable states it can occupy. The mind-bending proposal of the string theory landscape is that there are not just a few possible low-energy states for these fields, but an astronomically vast number of them. The mathematics suggests a number so large it defies human comprehension, perhaps 10 to the power of 500 distinct vacuum states. Each one of these unique configurations represents a different set of physical laws. In one bubble of this landscape, the Higgs field might settle at a value that gives electrons immense mass, making chemistry impossible. In another, the strength of the strong nuclear force could be too weak to form atomic nuclei, leaving a universe of only hydrogen. The cosmological constant could be 1 trillion times stronger than in our world, ripping spacetime apart instantly, or it could be negative, causing a swift and violent collapse back into a singularity. Our universe, with its specific, life-permitting constants, is simply one point in this cosmic lottery, one particular combination where the fields fell into a configuration that allows for stars, planets, and conscious life to emerge. We do not live in a specially designed cosmos, but in one that is habitable by pure chance, a single winning ticket drawn from an infinite pile of losers. This cosmic froth of universes could be continuously bubbling into existence, driven by the same quantum processes that might cause vacuum decay. Our entire observable cosmos might be one such bubble, a region where the fields tunneled into our specific, stable state, while beyond the horizon of our Big Bang, an endless foam of other universes with alien physics expands eternally, forever separated from us by an impassable barrier of inflating space. The multiverse transforms our deepest questions. We can no longer ask why the laws of physics are what they are, because there is no single answer. The question becomes why we find ourselves in this particular universe, and the answer is simple: we could not exist in any of the others. This idea is both humbling and liberating, suggesting that the ultimate reality is a vast, chaotic, and creative ensemble of all possible worlds, with our home just one fragile, shimmering bubble in an unending cosmic sea. We have traveled from the solid ground of a proven field to the furthest shores of cosmic speculation. 30 different windows into the invisible architecture of reality, from the Higgs molasses that grants us mass to the phantom energy that could tear us apart. We have explored how a single field might have tipped the cosmic scales to leave behind a universe of matter, and how another could be the ghostly answer to dark matter. We have questioned whether time is a fundamental river or an emergent illusion, and if the entire cosmos is a holographic projection. This journey reveals a profound truth, that the language of hidden fields is our most powerful tool for describing the deepest workings of existence. These are not just abstract ideas, they are the potential keys to unlocking everything. So tell me, which of these 30 theories reshaped your view of the cosmos? Was it the chilling possibility of vacuum decay, the elegant partnership of supersymmetry, or the mind-bending vastness of the multiverse? Let me know in the comments below. If you enjoyed this deep dive into the universe's hidden blueprints, Please give this video a like and subscribe to the channel for more adventures into the greatest mysteries of space and time.